All right. Good morning, Shamakara. I think
Good morning, sir.
So I'll be with you today. And others, I think smart students, they can study themselves. It's okay. Okay, first let me start. Maybe if more students come after that, I will tell you some details about your quiz, okay, and how to do that, how to submit it, and how to show your work, everything. All right, so let's start. In the previous chapter, actually, chapter 1, it was about vectors. Chapter 2, it was about systems of linear equations. Now we have another chapter. It's a little bit big chapter, and maybe one of the most important chapter in this book, because we are going to use them a lot. And also, we are going to use actually matrices and determinants and some concepts here in other courses. Okay. So this chapter is about matrix. So what we have here is 7 subchapters: matrix operations, matrix algebra, the inverse of a matrix, the LU factorization, subspaces, basis, dimension, and rank, introduction to linear transformations and applications. Each subchapter here is actually the big chapter. Anyway, guys, I will actually send your assignment soon for chapter 2. Okay. All right. So now let's start with matrix operation. And what is matrix itself, okay? And when we say operation, what operations can we do on matrices? Matrices like addition, subtraction, if it is multiplication, how is it defined, okay? And do we have division for matrices? And this kind of stuff. First, okay, guys, so far this. All right. First, let's start with the definition of a matrix. So far, actually, you are familiar with matrix, and also in chapter 2, right? Actually, we use matrices, as you remember, augmented matrices to solve a system of linear equations, okay? And so here, actually, we will learn matrices in its own right. All right, what is matrix itself? And how do we define addition of 2 matrices? How do we define subtraction of 2 matrices? And blah, blah, blah. So simply, matrix is defined as a rectangular array of numbers called the entries. That means that array of numbers, and those numbers in the matrix, it is called entries, or we call this elements of the matrix. So here, we have a bunch of numbers here. So this one is a rectangular array, right? Here we have an array of numbers, but actually they are placed here in rectangular order. Here, as you see here, if you just put in a box, it looks like a rectangle. That's why we say that a rectangular array is just not a single array here, right? So each number here, we have 3 and 1 and -2 and 0. And how you read, it's up to you, like 3, -2, 1, 0, or 3, 1, -2, 1. Actually, these are entries of the matrix here. Usually we use capital letter to denote matrices. I can just write here, this one is matrix A. Another example for matrix, let's say here we have some kind of matrix here. These are rectangular array of numbers. Those numbers are square root of 3, and here we have 4, here we have 1. Pi is also, actually, we know that it's a constant number. And here we have 0, 3/5. So these are the entries of these matrix. And how many entries does it have? It has 6. And so we know that actually by its dimension. Because as you see here, when you look at the matrix, it has rows. Right here, we have 2 rows, and here we have 2 columns. And how about this matrix? It has 2 rows, and it has 3 columns, 1, 2, 3, okay? So actually, we will give a special name to the number of rows and the number of columns of a matrix. Another one, I don't know why C is there. So we have some other examples for matrices. Let's say here C, and the 4, 3, 9. And also we'll give a special name because this matrix has only 1 column, right? So this one, it has 3 columns, and this one, it has 2 columns. And this one also, it has only one column. So we call this column matrix. Column matrix means now we know that actually we're talking about a matrix that has only one column. And how about this D? In D, as you see here, we have only one row. One row, how many columns? Here we have 1, 2, 3, 4. So if a matrix has only a row, then we call this a row matrix. It's like a row vector and a column vector. And how about in example E? It has 3 rows, right? And it has 3 columns. That's also one example for a matrix. Rectangular array of numbers. The first row, the second row, and third row, first, second, and third column. Okay, good. Now we know what is a matrix. Now, how about the size of the matrix? How do they find this? The size of the matrix is the description of the number of rows and columns it has. Okay, actually, we need to give a special name. How do we call it? Just a matrix. But as you see here, every matrix is actually different, right? As you see here, this one is, it has 2 rows, 2 columns. This one has 1 row and 4 columns. And this has 2 rows and 3 columns. This one has, example E has 3 rows and 3 columns, right? And the last one, C, it has only 1 column. So now the size of the matrix. What is it? It's a 1 by m matrix is called a row matrix. We have already seen this, or row vector. N by 1 matrix is called a column matrix or column vector, okay? And together, if we have, for example, if a matrix has m rows and n columns, we will call this m by n matrix. So this one is, what is it? A row matrix, because the first one, actually, the size of the matrix, the first number represents the number of rows of a matrix. So that means it has 1 row, m column. It is something like this. For the first one, here we have, let's say, matrix A, and here we have only 1 row and m columns. Let's say here we have something like this: A, 1, 1, A, 1, 2, A, 1, 3, dot, dot, and here we have A, 1, m. And these entries are real numbers. And why we are just using this, so actually we'll also give definition to this. We use subscript notation to denote the entries of a matrix, right? So that means that that number is in the first row and the first column. This one is in the first row and the second column. And this one is the first row. This should be 3. And the third column. So that is a row matrix. Then what is the dimension of, or the size of this matrix? That is just 1 by m matrix. And how about for the column matrix? Let's say matrix B. Here we have something like this. So let's say this one is B, 1, 1, the first row, first column. This one is B, 2, 1, second row, first column, dot, dot, dot. This one is B, N, 1, nth row, first column, right? And this one is, as you see here, this one is N by 1 matrix. All right. And double subscript notation. Here we have double subscript, not only single. Here we have IJ, right? That is subscript notation. That is double, because here we have 2 different indices here. Or capital AIJ. Notation is used to refer to the entries of a matrix. Okay. For example, here, if you just write here, capital A, that's the name of the matrix. All right. And here the entries are A sub IJ. That means that this I is changing from 1 to M, and J is changing from 1 to M, right? And if you just expand this, we mean like this. Here we have A11, A12, A1N, and here we have A21, AM1. And if I just pick any entry, for example, this AIJ, what entry is it? That means that that entry is located at row I and column J. Right, at row I and column J. So the diagonal entries of A are 1, 1, 2, 2, 3, 3. To write actually the entries in the diagonal of the matrix, actually the subscript notations, they should be equal to each other, right? This is 1, 1, 2, 2, 3, 3, 4, 4, and M by M. And these are actually M by N. If we have something like this, for example, let's say 1, 2, 3. And here we have 1, 2, 3. What are the entries in the diagonal? Actually, these are the diagonal, right? And actually, usually when we just talk about the diagonal entries, we mean square matrix. That means that M equals N. At that time, it is called a square matrix. So here, if M equals N, then A is called a square matrix. In square matrix, actually, we can just write all the entries in the diagonal, and those diagonals are these entries. All right. These are just simple definitions. A square matrix whose non-diagonal entries are all 0 is called a diagonal matrix. A square matrix whose diagonal entries are all 0, non-diagonal entries are all 0 is called a diagonal matrix. If you look at this, for example, D, it is a diagonal matrix because all the entries which are not in the diagonal, they are 0. That is 0 is not in the diagonal. There's 0, 0, 0, 0, 0, right? And here in the diagonal, they are not all 0. At least one of them is not equal to 0. Then we call this a diagonal matrix. And how about here? Also, this is another example for diagonal matrix, right? All the numbers in the diagonal and all the number entries which are not in the diagonal of the matrix, they are 0. A diagonal matrix, all of whose diagonal entries are the same, is called a scalar matrix. Okay. So here, a diagonal matrix, that means that all the entries which are not in the diagonal, they are 0. And all the entries in the diagonal, they are equal. We call them a scalar matrix. So as you see here, all the entries, this is a diagonal matrix. And more than that, all the entries in the diagonal, they are equal. So that is, what is it? A scalar matrix. And also this one, right? As see here, all the entries in the diagonal, they are equal. That's also example for diagonal matrix. If the scalar on the diagonal is 1, the scalar matrix is called an identity matrix. That actually should know this very well. We are going to use this a lot. In algebra system, actually in real number system, this identity matrix is like 1 because we know that A times 1 is equal to 1 times A is equal to, what is it? A. And also this identity matrix, usually we denote this by capital I. And you will see that soon, actually we'll use this a lot. If you multiply any matrix by this I, or I times A, that's equal to matrix A itself. And that's why it's called identity matrix. All right. And how about the equality of two matrices? When do we say that two matrices are equal? Actually, we say that two matrices are equal to each other if actually the dimensions or the sizes of these two matrices are equal and their corresponding entries are equal. For example, if you look at this two matrices, are they equal or not? What is the size of this matrix or order or dimension of this matrix? That is, it has 2 rows, 3 columns. So this one is 2 by 3 matrix. How about the B? It has 2 rows and 2 columns. This one is 2 by 2 matrix. For two matrices to be equal to each other, they must have the same size. See here, this one is 2 by 3 matrix, right? And this one is 2 by 2 matrix. That means that matrix A is not equal to matrix B. Another example, I need to write this a bit down. Okay. Just right here. This one is 2 by 3. This one is 2 by 2. So their dimensions or sizes are not the same. That means that these matrices are not equal. And how about C and D? What can we say about C and D? Actually, this matrix is 3 by 3 matrix, and this one is also 3 by 3. It has 3 rows, right? And it has 3 columns. And also the second matrix, it has 3 rows and 3 columns. So they have the same sizes. Now, also we have 2 conditions here. The second one is corresponding entries must be equal, right? Corresponding means if you just pick any entry from here, let's say it is Cij, is it equal to Dij? When we say corresponding entries, we mean this, right? See here, this entry 1, 1 corresponds this 1, 1, right? It is D11, C11. And this one, C33, corresponds this D33. Are they equal? Yes. And how about this one? C13 and D13. Are they equal? If you just look at these two matrices carefully, as you see here, all corresponding entries are equal. That means that now we can say that the matrix C is equal to matrix D. All right, another one. Okay, I think I can just write them here, 3 by 3, 3 by 3. So matrix C is equal to matrix D. And how about E and F? As see here, this one is 2 by 3 matrix. And how about this one? 2 by 3 matrix, right? And how about corresponding entries? For example, let's say E11 is equal to 2. And how about F11? The first entry, right? The first row and the first column, that's equal to 0. That means that E11 is not equal to F11. And other entries, we don't have to check because all corresponding entries must be equal to each other for two matrices to be equal to each other. That means that here, a matrix E is not equal to matrix F. You may see that actually, okay, 2, 3, 1, 2, 3, 1, 0, negative 2, 2, 2, negative 2, 2. Okay, actually, they look like the same, but they are not corresponding each other. I mean, those corresponding entries are not equal, right? So that's why these two matrices are not equal to each other. It's about equality of two matrices. Another one here, 3, 5, 7, 3, 5, 7. Okay, and the first glance, you can see that all these two matrices are equal. Actually, what is the dimension or size of this matrix? It has only one row. It is 1 by 3. And how about this one? This one is 3 by 1. And 1 by 3 and 3 by 1, these are different sizes. And this one is row matrix. This one is column matrix, right? If you're talking about maybe vectors, okay, if you're using this as a row vector or column vector, you may say that, okay, they are represented the same thing. But here our context is different. If you're talking about matrices, right? And these are not exactly the same matrices. And you will see that why is this so? Because actually for these two matrices to be equal, they must have the same size. And more than that, also the corresponding entries must be equal to each other. Guys, let's have a break for 1 minute. Let me make my tea, okay? After 1 minute, we will continue. Okay. The first operation about matrices, that is addition and subtraction of two matrices. How do we add or subtract two matrices? Number one, first, to be able to add or subtract two matrices, they must have the same sizes, right? The same orders or the same dimensions, okay? And just to add two matrices, we have to just add their corresponding entries. As you see here, we have A, matrix A, it is Aij, and matrix B, Bij, and we want to add these two matrices. So this A plus B is Aij plus Bij. And of course here, we don't know the dimensions of this matrix. If actually this A is, let's say, M by N matrix, and also this must be M by N matrix. Otherwise, we cannot. Actually, this addition is not defined if two matrices have different sizes. Then here, that means that this I is changing from 1 to M, right? And how about this J? J is changing from 1 to M. When actually these numbers change from 1 to M and 1 to N, that means that we are adding all the corresponding entries. And also for subtraction, the same thing. To be able to subtract two matrices, they must have the same dimensions or sizes. Then just we subtract their corresponding entries. For example, let's say we are given two matrices here, matrix A, which is 2 by 3 matrix. This one is 2 by 3 matrix, right? So actually we have no problem with their sizes. That means that we can subtract these two matrices or add these two matrices. If we add, for example, A to B, here we have A plus B, that means corresponding entries here 2 plus negative 2, that's equal to 0. 5 plus 9, that's equal to 14. 1 plus 0, that's equal to 1. Done. How about the second row? Negative 7 plus 12, that's equal to 5. 3 plus 6, that's equal to 9. And 1 plus negative 1, that's equal to 0. So we have just added these two matrices together. How about subtraction? If you subtract B from A, that is A minus B. So I have to subtract negative 2 from 2. 2 minus minus 2, that's equal to 4. And 5 minus 9, that's equal to negative 4. And 1 minus 0, that's equal to 1. Negative 7 minus 12, that's equal to minus 19. And we can actually just continue subtraction in this way. Okay, and how about the next thing is, actually first title should appear, scalar multiplication. That means that how do you multiply a matrix by a scalar, a real number, right? So here the C is a real number. So here we have the C is, what is it? A real number. Maybe 1, 2, 3, 4, 5, 6, 7, anything. Okay, how do you multiply a matrix by a scalar? To do this one, just simply, let's say if we need to multiply matrix A by C, so that means that we need to multiply each entry by C. Right, it's C times Aij. This is how we actually show this in a compact, using a compact notation. For example, let's say we are given matrix A and matrix B, right? That first we need to multiply matrix A by 3. That means that we need to multiply each component, each entry, each entry or element by 3. So 3 times 2, that's equal to 6. 3 times 5, that's equal to 15. 3 times 1, that's equal to 3. In a similar way, we can just multiply all the entries in the second row. 3 times negative 7, negative 21, 3 times 3. And in the same way, how about if we need to multiply B, matrix B by 1 over 3? So we should multiply each entry by 1 over 3. 1 over 3 times 3, that's equal to 1. 1 over 3 times 6, that's equal to 2. 1 over 3 times 9, that's equal to 3. 1 over 3 times 15, that's equal to 5. Right? This is how we multiply a matrix by a scalar. Okay. Good. Now, actually, guys, this addition and subtraction, as you know, that they are just simple, and also performing this operation over matrices, it's not so difficult. But usually in multiplication, if you have never seen this, it may look a bit weird. And I know that you already learned this before. That's why I think you have experience. But usually for the students, if they're actually learning this for the first time, it's a little bit challenging for them. So because matrix multiplication is a bit different. And also now immediately you will see that for multiplication, A times B is not equal to B times A. And this shows that it is not similar to multiplying one real number by another real number. Okay. All right. So how do we actually define the multiplication of two matrices? If A is, the matrix A is an M by N matrix. And immediately what we mean by this, it means that the matrix has M rows and N columns. And B is an N by R matrix. If you just notice here, intentionally, I am using the same variables here, N and M. That is the only way that actually we are able to multiply two matrices. If the number of columns of the first matrix is not equal to the number of rows of the second matrix, then multiplication is not defined. We cannot multiply. To be able to matrices, the first matrix, let's say this is A times B, the number of columns of the first matrix must be equal to the number of rows of the second matrix. Then we can multiply this. And so the product C, which is equal to A times B, will be of this size. As see here, this will be M by R, the size of the product C. It will be M by R matrix. And the ij entry of the product is computed as follows. So let's see ij. What are like the elements of this product C? The Cij is just equal to this sum. Now I will actually show this in example. What we are doing here, actually to get the ij entry of C, right? We're just multiplying. Actually, that is dot product here. As you see here, it looks like a dot product. We are multiplying. What is it? Here, I1, right? And I2 and the IN. What are these? If we look at these A's, right? What are these? This one is I's row of matrix A. And how about this B? B1J, right? B1J, B2J, and BNJ. These are J's column of matrix B, right? And if you just multiply them together, it gives us Cij entry of C. That means that to do this one first, we should know how to multiply a row matrix by a column matrix. Here we are just multiplying a row matrix by column matrix. So that means that, for example, let's say I'm given this matrix. Here we have 1, 2, 3. Okay, what is it? Row matrix. And let's say we should multiply this by 2, 1, 5, for example. And what is the size of this matrix? 1 by 3. And how about this one? It is 3 by 1. Multiplying row matrix by column matrix. As see here, 3 and 3, they are equal. And the resulting matrix will be of size 1 by 1. How do you multiply this? Here, this form is saying that to multiply a row matrix by a column matrix, just multiply the first entry by the first entry. That is, here we have 1 times 2. The second entry by the second entry, 2 times 1. And third entry by the third entry. It is 3 times 5, which is equal to 1 times the 2, 2 times 1 is 2, 4, 4 plus 15, that's equal to 19. So the resulting matrix here will be 19. Okay. So that means that here, let's say this matrix, this one is 2 by 3, right? And this matrix is 3 by 2. The number of columns of the first matrix is equal to the number of rows of the first matrix. That means that we can multiply these two matrices. And here we have 2, and here we have 2. The resulting matrix will be of size 2 by 2. So that means that if you multiply here A by B, we will have C, right? So the C will have something like this. It will be 2 by 2 matrix. Here we have C11, C12, C21, C22. We will have these matrices, right? And now, according to this definition, it's saying that if you want to get C11, what is C11? And to get this one, here 1, 1. Multiply the first row of A by the first column of B. And what is the first row of A? That is 2, 5, 1. And first column of B, that is, what is it here? The first column of B is 1, 2, 0. That is 1, 2, 0. Now, from here, we know how to multiply a row matrix by a column matrix. If you multiply this, 2 times 1, 2, 5 times 2, 10, 1 times 0, 0. Here we have 2 plus 10, that's equal to 12. So this C11 is equal to 12. And how about here, let's say C12. Again, the 1, 2, right? That means that the first row of A, that is 2, 5, 1. We should multiply this by the second column of B. The second column is 3, 0, negative 2. So 3, 0, negative 2. So if you multiply this 3 times 2, it is 6 plus 5 times 0, it is 0. 1 times negative 2 is negative 2, which is equal to 4. Now, we know the value of C11 and C12, right? Those are 12 and 4. So how about How about, for example, C21? I can evaluate this somewhere there. Okay, let me just change marker color. I can do that here. For example, C21. C21 is the second row of the first matrix, the first column of the second matrix. What is the second row of A? That is negative 7, 1, 1. So it's negative 7, 3, 1. And we should multiply by the first column. The first column is okay, this one is 2 by 3. Oh, that's been my one mistake here. And the second matrix here is 3 by 3. This one is 3 by 3. So this 3, 3 are equal. So the resulting matrix will be 2 by 3. So here we will have 2 by 3. That is C1, 3, C2, 3. So we will have this thing. And also here I need to multiply to 1 by 3. Okay. Good. All right, let me just separate this example so that we'll have more space because it's a little bit messy here. Okay. And I will maybe redo this. All right, we have 5 minutes. Let's finish this. So, so this one is, okay, 2 by 3 matrix. This one is 3 by 3. So if you just multiply here A by B, we will have C, whose actual size will be 2 by 3. That is C11, C12, C13. They are all in the first row. That's why the first subscript notation is 1. Now the second row, it will be C21, C22, C23, right? Okay. Now we need to get C11. So to get C11, we need to multiply the first row by the first column. So that is 2, 5, 1. That is multiplied by 1, 2, 0, which is equal to 2 plus 5, that's equal to 12. And C12, that means we need to multiply the first row by the second column, right? That is, second column is 3, 0, negative 2, 3, 0, negative 2, which is equal to, it is 6, this 0, negative 1. So here we have 4. And how about C13? The first row, 2, 5, 1 by the third column. That is 1, negative 2, 5. The third column of B, which is equal to 1 times 2. It is 2, negative 2 times 5, negative 10. 5 times 1 plus 5. It is negative 8 plus 5, that's negative 3. So now we got the first row. Okay, I can just write here. Let me just write here then. The C that's equal to A times B will be something like this. So the first row entries are 12, 4, negative 3. So here we have 12, 4, negative 3. So how about the second row? So that is C2, 1. Here we have C2, 1. That means that we need to multiply the second row of A by the first column. Second row is negative 7 and 3, 1. Multiply this by the first row, 1, 2, 0. So 1 times negative 7, negative 7. 2 times 3, it is 6. And plus 0, that's equal to negative 1. So here we have negative 1. And how about C2, 2? That's again second row by the second column, negative 7, 3, 1, multiplied by the second column, 3, 0, negative 2, which is equal to 3 times negative 7, negative 21. 3 times 0, it is 0. 1 times negative 2 minus 2, which is equal to minus 23. And how about C2, 3? Again, the second row, negative 7, 3, 1, and multiplied by third column, right? That is 1 minus 2, 5, which is equal to 1 times negative 7, negative 7, 3 times negative 2, negative 6, 1 times 5 plus 5, which is equal to minus 13 plus 8 minus 8. So the entries in the second row will be -1, -23, and the -8. So these are the entries of the product C. Okay, and that's how we multiply. That is how we should understand the definition. Okay. And just for your information, how do we multiply two matrices in Excel? Actually, to do this one, of course, also we should know actually you are multiplying two matrices. Number one is it defined or not? Number two is you have to select the destination cells. Then actually pressing F2, press Control plus Shift and Enter together, we can multiply. Okay, so from here we will continue next session. Have some break, 10 minutes break. Okay, I will see you after 10 minutes.